We'll wrap up our overview of Java's key functional programming concepts and features by exploring case study ex2. In this case study, we'll walk through code that computes big integer factorials in various ways, some buggy and some correct. The code we'll walk through is available in my ex2 project in the FP folder in my Modern Java GitHub repository. We're now in my IntelliJ project for case study ex2. This program implements various ways of computing factorials for big integers to demonstrate the performance of alternative parallel and sequential algorithms. It also shows the dangers of sharing unsynchronized mutable state between threads, as well as the overhead of incurring excessive synchronization. It illustrates both Java sequential and parallel streams. Let's start by taking a look at the two fields defined in the ex2 class. The first field is called smax iterations. It's a static final int that defines the total number of iterations to run the timing tests, and we set this value to be 20,000. Next, we define another static final int called sDefaultN, which is the default number to compute for factorials, which we set to 1,000. Let's now take a look at the main entry point into the test program. The first thing we do in here is we initialize a local variable n of type BigInteger to be the default value or a value passed in on the command line in argv sub 0. Once that value is set, we warm up the fork join pool to ensure we have accurate timing for all the different tests that are about to happen. Next, we run the various factorial tests. There are 4 tests that we run, and before we look at the code in detail, we'll talk briefly about what each test is doing. The first test, which is called sequential stream factorial, provides a baseline factorial implementation using a Java sequential stream. The next test, called Buggy factorial, demonstrates how race conditions can occur when state is shared between worker threads in the Java common fork join pool using mutable shared objects. We'll also see this used as a Java parallel stream incorrectly. The third test shows how a synchronized statement can be added to avoid race conditions when state is shared between Java threads, but it does it in an inefficient way. And we call this test the synchronized parallel factorial test. And the fourth and final test is the parallel stream factorial test. And this shows how the modern Java reduce operation can be applied to avoid sharing state between Java threads altogether. Each of these tests is called in the context of a helper method called run test, which we'll look at in a moment. As we'll see, the run test method keeps track of the timings of all the different tests, and at the very end, we print the timing results in descending order from fastest to slowest. So before we actually take a look at each of the factorial computations, let's first look at the run test helper method. As you can see, this run test method runs the factorial test, which is given here as a function, in order to be able to compute the factorial of n and print the results. So the first thing that we're going to do here is we're going to run the garbage collector to ensure that each of these tests starts with all the memory. They all begin in somewhat pristine state. Next, we're going to use a little helper class and a helper method in that class called timeRun. And that's going to go ahead and time the amount of wall clock time taken to run the test. Let's go take a quick look at the timeRun method in the run timer class. You can see this version of timeRun takes in a runnable and a test name. And the first thing it does is it starts the timer, so it goes ahead and records the current system time. Next, it calls the run hook method on the runnable that's passed in order to be able to perform the test. And then the final thing it does in this little snippet of code is stop the timer, which figures out how much time it took to execute that particular test. And that result is then stored in the results map, which is a map that maps the string name to the time taken to perform a test. And that time that executed is put into the results map under the test name. And we'll see how that gets printed out when we're done showing off all the different code and running the example. What we do here is we make an int stream running from 0 up to smax iterations. So it'll run smax iteration times, effectively a functional for loop, if you will. And for each of these iterations, we're going to go ahead and apply the factorial function passing in the parameter n. And when that's done, of course, we will go ahead and print out what we get back, which is going to indicate how this worked by applying that particular function for that particular value of n. So now that we've given an overview of the run test helper method, let's go ahead and start all the tests to run. And it'll take a few minutes to run, but while it's doing that, let's go ahead and continue on walking through the code. So we'll start by taking a look at the sequential stream factorial class, and that provides the baseline implementation that uses a sequential Java stream. As you can see here, here's the factorial method. It's defined to be static. It takes in the value n. The first thing it does is it creates a stream of longs from 1 to n using the ranged close method on long stream. Next, we use the map to obj intermediate operation to convert each long into a big integer, which is that arbitrary precision integer we've talked about before. And then the final thing we do here is we use the reduce operation, passing in an initial value of 1, and then calling multiply to do pairwise reduction of each of the different elements in that stream. And so what we'll end up with when all is said and done is we'll end up returning the value of n factorial computed using a sequential Java stream. Let's now turn our attention to the Buggy factorial implementation, which demonstrates how race conditions can occur when state is shared between worker threads in the Java common fork join pool via a shared mutable object and the for each terminal operation. We'll start by taking a look at the nested class total that occurs within the Buggy factorial class. This class attempts to keep a running total of the factorial, and it provides a sadly buggy method for multiplying this running total with a value n. At the root of the problem is this field mtotal, which is attempting to keep track of a running total of the factorial. However, it's shared mutable state that's not properly protected by any synchronizer. It's given the initial value of 1. Here's the multiply method, which takes a parameter n of type BigInteger and multiplies mtotal by n and then updates mtotal. However, because this method contains no synchronization, there will be race conditions incurred when it's run on a multi-core processor. So let's see how that occurs down below. Here's the actual factorial method on Buggy factorial. It also takes a big integer n, and it attempts to compute the factorial for this value. The first thing that the factorial method does is it creates a local variable t of type total. And this object is incorrectly shared by multiple threads in the Java common fork join pool. Let's see what happens next. Once again, we create a stream of longs from 1 to n using the ranged close method on long stream. We then run these in parallel, and this is where things start to fall off the rails. We then apply the map to obj intermediate operation to create a big integer value from the long values in the stream. So we have a stream of big integers coming out of map to obj. And then here again is where things really fall apart. We call the for each terminal operation, which is attempting to multiply the values in the stream using the single non-synchronized shared mutable object t. And that's where things really go awry, because this call to t multiply, unfortunately, will result in updating this shared mutable state, which is not protected by any synchronizer. And as you'll see when we look at the results, they're all over the place. The final thing we do here is we return the value of mtotal, which is also a problem because it's not synchronized either. So there's very likely to be visibility issues when memory is shared between cores in a single multi-core processor. So this is what not to do. It might be tempting to think we can solve the problem with the Buggy factorial by applying the appropriate synchronizer in the implementation. However, this leads to a different set of problems. So to show that, we'll take one more detour before we show the final correct solution by examining the synchronized parallel factorial class, which shows how a synchronized method can avoid race conditions when state is shared between Java threads, but unfortunately it does it in a very inefficient way. So this particular code looks pretty much identical to what we had before, with a couple of small changes. Instead of having an unsynchronized multiply method, we apply the synchronized keyword, thereby ensuring that only one thread at a time can be calling multiply, which will ensure that we synchronize access to updating mtotal. Likewise, we also add a get method on the total class, which is synchronized as well, and that returns mtotal in the context of a synchronized call, which is used to ensure the visibility of the data. If we take a look at the rest of the code, you'll see it's quite identical to what we had before. And when we take a look at the results shortly, you'll see that even though this produces the correct value, the correct factorial value, Unfortunately, it's very, very slow. Now that we've seen a couple of implementations that either incorrectly or inefficiently compute the nth factorial, let's take a look at the parallel stream factorial implementation, which shows how the modern Java reduce operation can be applied to avoid sharing mutable state between Java threads altogether in the context of a parallel stream. This implementation is almost identical to the sequential stream factorial class we looked at earlier. The main difference being, of course, that rather than running the stream sequentially, we add the .parallel operation after we create a stream of longs from 1 to n. This causes the stream operations to run concurrently in the common fork join pool. As before, we call the map to obj intermediate operation to convert the long values into big integers, and then we call reduce. This time we're going to call a slight variation of reduce, which takes 3 parameters. In this particular implementation, we pass in the value of 1 to be the starting point for the reduction, and then we have the second parameter, which is big integer multiply, which is treated as something called an accumulator. And then the third parameter, which is also the big integer multiply method, is called a combiner. And notice that when we do this, reductions are performed on the stream in parallel. However, there's no shared state at all because big integer is creating immutable objects which are being pairwise reduced together to create a final result for the nth factorial. The first half of the results show the factorial for 1,000 returned from each of the methods. As you can see, the sequential stream factorial and the synchronized parallel factorial and the parallel stream factorial methods all returned the same results. These results go on forever and ever because the 1,000th factorial is very large. In contrast, the Buggy factorial was different and incorrect. So clearly there were problems due to the race conditions we talked about when we walked through the code. The second half of the output print the results from fastest to slowest from running the 4 factorial classes. As you can see, parallel stream factorial executed the fastest, taking about 1,360 milliseconds to perform the 1,000th factorial computation. In contrast, the sequential stream factorial was about 2.5 to 3 times slower, taking 3,360 milliseconds, and the synchronized parallel factorial was much slower, about 5 times slower than the parallel stream factorial, taking over 6,000 milliseconds to run. And that was due to the contention from having that synchronized method protecting the m total field. Of course, Buggy factorial executed relatively quickly, but that's because it was buggy. So it didn't really matter that it gave a fast result, it gave the wrong result. So the bottom line here is that by using modern Java features such as reduce in the context of parallel streams, we can get good performance and the right results without having to write complicated code. So that's the end of our lesson that provides an overview of Java's key functional programming concepts and features, focusing on a case study that computes big integer factorials in various ways.